Newton's laws and momentum. Newton's first law states that a body will remain at rest or continue moving at a constant velocity unless an external force acts on it, which is just a specific example of the second law. Newton's second law states that the net force on a body is proportional to the rate of change of its momentum. Because of the definition of the Newton, the constant of proportionality is 1, so the net force on a body is equal to the rate of change of momentum. Therefore, F equals ma is a special case of Newton's second law as you can see. When the force is 0, the body's momentum, and hence its velocity, will not change.
Newton's third law states that when bodies interact, the forces they exert on each other are equal in size and opposite in direction. This might also be familiar to you, as for every action there is an equal and opposite reaction. When looking at a forces diagram showing the forces on the two bodies, it's easy to see two equal and opposite arrows and think that they cancel each other out. But because the forces are acting on different bodies, the forces don't cancel out. The momentum of a body, which we encountered in Newton's second law, is defined as the product of its mass and its velocity. Because mass is a scalar quantity and velocity is a vector quantity, momentum is also a vector quantity, so it has a direction. When bodies interact with each other, usually by collision, then the total momentum is conserved, and because it's a vector quantity, it's conserved in any direction. If the kinetic energy in the collision is also conserved, so the total kinetic energy afterwards is the same as the total kinetic energy before, then a collision is described as elastic. But usually, in real life, kinetic energy is lost, so the collision is described as inelastic. Now, using the Newton's second law equation, which is F equals delta P of delta T, you can rearrange that to give F delta T equals delta P, so the force times the time that the force is applied for is equal to the change in momentum of the body. The quantity force times time is described as the impulse, and if you draw a graph of force against time, the impulse is the area under the graph. So on to some questions. To start with, we have some straightforward definitions. We're asked to state the principle of the conservation of momentum, so we need to say that when two bodies collide, the total momentum before is equal to the total momentum afterwards. It's important here to state that we're talking about the total momentum, and also the mark schemes like to see the word collision or interaction in there of some sort, so you have to imply that the bodies aren't just sitting there beside each other. Next, we have to say what an inelastic collision is, so that's quite simply kinetic energy is lost, because kinetic energy isn't conserved. So now we have to actually do some sums with momentum. So we've got these two blocks moving towards each other, and they stick together and then move off with an unknown speed, which we need to find. So the first question is to find the speed, and using the conservation of momentum, we know that the total momentum before is equal to the total momentum afterwards. So we can write those things down, set them equal to each other, and then solve to find the speed. So the total momentum before is 2.4 kilograms times by 3 meters per second, then plus the 1.2 kilograms times by 2 meters per second. However, because this is moving in the opposite direction to the other one, its velocity is negative. So if we take moving to the right as positive, then this block over here has a positive velocity, this one has a negative, and these ones over here will also have a positive velocity. So the total velocity before on the left here is equal to the total momentum afterwards. So that's the total mass, which is 3.6, times by the speed v, which is unknown. Now if we add up all these things on the right, 2.4 times 3 plus 1.2 times by negative 2, that comes to 4.8. So 3.6v equals 4.8. Well, if you divide through by 3.6, 8 divided by 3.6, then you will get the speed, which comes out as 1.33 meters per second. Now we have to show that the collision is inelastic. So if it was elastic, then the kinetic energy before would be equal to the kinetic energy afterwards. So to show it's inelastic, we have to show that's not the case. So we just add up the kinetic energy before, add up the kinetic energy afterwards, and show they're not equal. So the kinetic energy before, using all the data we have, is just the sum of both of their kinetic energies, so half mv squared for each block, half times 2.4 times 3 squared, plus half times 1.2, do that, times 1.2 times by 2 squared, of course. When you add that up, 0.5 times 3.4 times 3 squared plus 0.5 times 1.2 times 2 squared. It's important to note here that the 2 is not negative, as it was before, because to find the kinetic energy, we're only interested in the speed, not the velocity, so direction doesn't matter. But even so, if you did minus 2, when you square it, you'll get 4 anyway, so it doesn't matter. So that comes out as 3.2 joules of kinetic energy before. Kinetic energy afterwards, we'll need to use our answer to the previous part. So it's half times 3.6 times by 1.33 squared, which comes out as 0.5 times 3.6 times 1.33 squared, comes out as 3.18 joules. So 13.2 is not equal to 3.18, that's obvious, so the collision is inelastic. Here we have a helicopter, and the helicopter is hovering, as it says, let's see, hovering here, and it's hovering by pushing air downwards. So we need to find the mass of air that it propels downwards in 5 seconds. So we're modelling that air as a cylinder of radius 5 meters, which is the radius of the rotors here. So we have the density of air. So the first thing to note is that density, that's an awful low, density is mass over volume. So if we want the mass, we're going to do the volume times by the density. That will be useful. So the volume of the air is what we need to find, as we're given its density. So we're modelling it as a cylinder, so the volume will be the surface area of this end times by the length. So the surface area of the end is a circle, so it's pi r squared, r is 5, times pi times 5 squared, and then times its length. So we want the volume of air propelled down in 5 seconds. So it's propelling the air down at 12 meters per second, as it says here. And so in a time of 5 seconds, it will propel 5 times 12 meters. It will propel 5 times 12 meters per second, meters of air. If that even makes sense, which it doesn't. But every second it propels air down 12 meters. So in 5 seconds, it'll be 60 meters. So that will be the volume, and then we can work that out itself, or because we just want volume times density, we can then just times straight away by the density to get the total mass. So pi times 5 squared times 60 times by 1.3 comes out as 6,130 kilograms to 3SF, which is about 6,000 kilograms, as we were asked to show. Calculate the momentum of this mass of descending air. Well, that's nice and straightforward. Momentum is mass times velocity. We've just worked out the mass, 6,130, times by the velocity, well, that's awful, times by the velocity. From the previous slide, we know the velocity is 12 meters per second, so we're simply doing 6,130 times by 12, which comes out as about 73,500 kilograms meters per second, which is an awful unit if any person. Add on kilograms meters per second. So the force provided by rotating helicopter blades, well, this is using Newton's second law, which states that F is equal to change in momentum, delta p, over the change in time, delta t. So we've just worked out the momentum of air propelled downwards, in 5 seconds. So that's the momentum up here, and we know the time is 5 seconds because that's the whole premise of the question. So we can just do that momentum. 7,000. Let's zoom in first, so it makes sense. 73,500 divided by 5, and that comes out as 73,500 divided by 5 is 14,700 newtons. 14,700, not 700. Equals 14,700 newtons. There we go. Now, the mass of the hovering helicopter. This is using Newton's third law. The force provided by the helicopter on the air, which we worked out here, is the same as the force provided by the air on the helicopter, which is keeping it hovering. Because it's hovering, that's the key word here, its net force is 0, so the force provided by the air on it is equal to its weight. So we can say that its mass times g, which is the weight, let's just put that over here, W equals mg, from G481, and that is equal to the force it provides on the air, 14,700 newtons. So divide throughout by G, 9.81, and we get about 1,500 kilograms, so about 1.5 tons, which is a reasonable mass for a helicopter, just a bit bigger than a car. That's 1,500 kilograms, and there we go.
The next question is to do with momentum. We've got to state the effect a net force has on the motion of an object. Quite simply, force changes the acceleration of the object or the momentum of the object. And then define the impulse of a force. Impulse is force times the time the force is applied for. Force F is applied to an object. The graph in figure 1.1 shows the variation of this force with the time t. The initial velocity of the object is 0 and its mass is known. Explain how this graph can be used to determine the final velocity of the object. So the area under the graph is equal to the impulse. So the final velocity is the area under the graph divided by the mass. The final part of this question is about a tennis ball being hit by a racket. The mass of the tennis ball is start. During a serve, the racket head and the ball are in contact for 4.2 milliseconds. So we're asked to calculate the mean force provided by the racket on the ball, and the mean force multiplied by the time is equal to the increase in momentum. So the mean force is equal to the increase in momentum divided by the time, which is 720 newtons. Now, to estimate the mass of the racket, the change in momentum of the ball is equal to the change in momentum of the racket, and because we have the mass of the ball, we can calculate the change in momentum, and we have the change in velocity of the racket, and so we can calculate the mass of the racket to be 500 grams or 0.5 kilograms. And the final part of the question asks why the value of this mass might be different to the actual mass of the racket. And the answer is that the person holding the racket will also have an impact on the change in the momentum during the contact of the ball.